Okay, back again for more Regents Common Core Geometry solutions and explanations. So this is the, which one are we on here? Let's see, August 2016 exam. So yeah, number 13, the cross section of a regular pyramid, okay, contains the altitude of the pyramid. Basically what that part means right there is the plane that we're using to cut the pyramid, that goes through that highest point right here. Okay, so the plane that passes through that vertex at the top. All right, so when that happens, what they're trying to show right here, okay, is that is the surface that got exposed when we cut through the pyramid. So that's going to be a triangle. All right, so the next one, diagonals of a rhombus, TEAM, intersect at P. And when you get a problem like this, probably the best move is to go ahead and take your scrap graph paper at the back of the packet, Regents packet, and just go ahead and make your own axis on that. Okay, you don't have to use up the whole thing, but go ahead and make your own axes and go find the point 2, 1. TA has this equation. Okay, right there. All right, perfect. Use your straight edge so that you're not, making any mistakes here. So what I did was I graphed TA. Okay, y equals negative x plus 3. The reason I started up there was the y-intercept is 3. Go up 3 on the y-axis, start there. And then the slope is the number in front of x, so it's negative 1. That tells me to go down 1, right 1. Or possibly you could go up 1, left 1. Okay, so that's how I got this line, and that's what it looks like. Now, we don't know how far along the diagonal T and A are. We just know they're somewhere on this, and this is, that's where the diagonals intersect. So, here's what we need to know. For a rhombus, the diagonals have to bisect each other, but they also have to be perpendicular. Okay, so that's for a rhombus. All right, so what we're looking to do is get a perpendicular line. So when you're on a graph, and this is something that my students, work on a lot, and they have some great ideas, they try to use their compass tool here and construct the perpendicular bisector. Not a bad move. I just tell them that's probably not what is intended here. When it's on a graph, you're supposed to be looking at slopes, distances, midpoints, things like that. So what they want you to do is looking at the slopes here. To get perpendicular, we need slopes that are negative reciprocals. So even though it's a good idea to use multiple tools, you could mess up if you try to do the construction of a perpendicular bisector. Instead, let's go through and use what's intended on this one, which we have to get the slopes or negative reciprocals. So the slope of EM should be, take this and flip and change the sign. So the reciprocal is 1 over 1, but then change the sign from negative to positive. So here's what we're saying. Go to here, go up 1, right 1, and that is going to be the start of your line, or go down 1, left 1. Okay, so that's what we have. All right, it's best to graph. We could always do it algebraically, but that is our information that we needed. So the slope is positive 1, the y-intercept is negative 1, and it looks like that is our choice. So choice 1. All right, moving on. Sorry. Okay. So, all right. So they're trying to push us off the graph a little bit. So all I'm going to do is I'm going to use my scrap graph again, and I'm just going to kick the x-axis down further and that'll allow me to move up to 12. There's other ways to do that if they push it even further, you know, say they use something like 30. So 3, 4, and 3, 12. And that is what, B, and this is A. Okay, now, what could be the coordinates of C? All right, so here's what we should look at right now. We know the area is 1/2 base times height if we have a right triangle, okay? If we don't have a right triangle, you know, we would use the A equals 1/2 AB sine of C formula. But I'm pretty sure on a graph we're going to be able to do this. So what we could do is figure out the length of this side. Right, that's going to be 8. Okay, basically from 12 to 4 is 8 units. Okay, now we've got to find the height basically. All right, let's call that the base and we'll find the height. Now, what we'll do is, since the area has to be 24, we'll replace A with 24. The base is 8 and we're looking for the height. Now, we have to create a height of 6 in this problem. So here's what I'm going to do. I'm going to go from here, 1, 2, 3, 4, 5, 6. My third point, my C, is either somewhere on this line, x equals 9, or it's this way, 6. Or it's over here at x equals -3. And it really doesn't matter where we put it. Okay, here's what I'm saying. The area, let's say we take a look at it like this. If this is 8, and we come up here, it doesn't matter if we put the point there, or we slide it anywhere along here. Okay, it's not going to make any difference on the area. Okay, all that's going to matter is that height and the base. Okay, so as long as that's 6, it doesn't matter where we place this third point along that line. Okay, and that's essentially what I'm saying. So anywhere on x is 9 or anywhere on x is -3 will give us an area of 24 square units. So that's what we're looking for. This looks good. X is -3. And for these, none of them, x is not 9 for any of them, or -3. So let's check this out. So let's go to -3, 8. If we went right there, what we would have is a base of 8 and a height of 6. So when we apply 1/2 base times height, we would get what we were looking for, 1/2 times 8 times 6. That is 24. This point, C, could have been anywhere along this line, and it would have worked. So that's our choice, is choice 3. All right, next one, we are looking to, okay, we want to get this equation to this format. Okay, x minus h squared plus y minus k quantity squared equals r squared. That is called center radius format, and then we'll be able to read the center radius. So we got to use a method called completing square. You know, of course, that's one way. There's plenty of ways to do this, but this is probably our most efficient way. So what I like to do is I like to take all the x terms, and I'm going to put a blank there. Whatever number goes there, that's what's going to complete the square. All right, now we'll start on y. So plus y squared plus 8y plus, again, I'm going to need a space there. I keep the plus 11, and whatever I add to the left side, I have to add to the right side. So I'm going to add something here, I'm going to add something there. So give myself 2 blanks there. All right, here's what I like to show my students. I don't know what this is yet, but whatever happens, I'm going to have x plus or minus something squared. Okay, I'm going to have, from these 3, I'm going to have y plus or minus something squared. It's going to be plus 11, and then we'll have something over here. Now, what we've noticed is if you cut this in half, whatever that term is, all right, -4, you're going to cut that in half and put in a -2. And then how do we fill this in? Well, we're going to have a negative 2 times negative 2 is positive 4. So that is the number that is needed to complete the square. So I added it over to the left. I should keep it even. Remember, we're trying to keep, this says equal, so if I want to keep it equal, I got to balance. I added 4 to the left, I better add 4 to the right. Same concept over here. Cut this term in half, so it's plus 4. 4 squared is 16, and keep it even, right? If I add 16 here, I got to add it over there. All right, 4 plus 16 is 20. I'm going to subtract 11 from both sides. All right, and finally, I have it in what we call center radius format. Now the center basically is whatever makes these both 0. So 2 for x will make that go to 0. Negative 4 for y will make that go to 0. And the radius is whatever the square root of that is. Happens to be 3. 2, negative 4, and radius of 3. Whoops, I picked the wrong one. Sorry about that. That's not the one I wanted. 2, negative 4 is this one, and a radius of 3. So that's number 16. 17. Great, a density problem. All right, so let's take this and we'll just pull that information out. Okay, that's 752 kilograms for every 1 meter cubed. Now, I like to, note that science does a really good job of this dimensional analysis. They pay close attention to units of measure. If we paid closer attention to units of measure, these problems would go a lot easier. Okay, so we're gonna show that a little bit here. What we want to do is Oaktree, circumference, height. Okay, so we're trying to model. We're doing a couple things in this problem. They're trying to say, how would you model a tree? Well, the closest figure that we study would be a cylinder. It's the closest fit, the closest model to a tree. Okay, so they didn't even give us the radius. They're making us work for the radius. They give us the circumference is 4.5 meters. It's good that it's in meters at least. And the height is going to be 8 meters. Okay, so we don't have to worry about units of measure change there. Now the volume of a cylinder is pi r squared h. We're going to have to work for r. All right, let's try this. A formula, we could use 2 pi r for circumference. Replace it with 4.5. Now be careful when you do this. You have to divide by 2 pi. Make sure your calculator is set right to do this, okay? You either have to put in parentheses or use like this key for an inspire, so that it's doing the big fraction for us. Or if you don't have the inspire, make sure you put the 2 pi in parentheses. Okay, when we do that, what we get for, let's see, the radius, I get 0.71, 0.71619. That's what I get for a radius. Okay? Now, I have to go back up to the volume formula. Let's just get a little space here. Go back up to the volume formula. And 0.71619 squared times the height of 8. And what does that give me? It looks like 12.89. Oops. And that's meters cubed. Okay? Now, of course, that's not it. We have to apply now the density to get the kilograms. Okay. So, I always like to do proportions, but to do multiple conversions, you're probably better off using science, which does dimensional analysis. I'm going to use what I've shown my students. So I'm going to set it up as 652 kilograms to every 1 cubic meter. I'm going to say x kilograms. We're going to search for that. We don't know. And it's to 12.89 cubic meters. So when we cross multiply, 1 times x is x. Let's ignore the units of measure for just a minute. And whatever 752 times that 12.89 is, Okay, when I look at that, let the calculator do the work. I get 9694.45. Okay, so that's as close as we want to get right there. All right. Let's see. Okay, so again, for this, I'd probably go back again to, the scrap graph paper. Okay, that's just how I like to do these. They're both going to fit on the graph. Why not just use the graph? Okay. Let's see, move. All right. No, it's not going to cooperate, so. All right. I'll just go right here. Go ahead and make your axis. All right, what do we got? Negative 6, 2. Sorry, negative 6, negative 2. So negative 2. Let's make sure. So there is x, right? And we got to go grab y, 6, 7. There's y. All right, and we've got to cut the segment into a ratio 1 to 5. So this is that partition of segment. Uh, 1 to 5 ratio, this should tell us to get 6 equal parts. Okay, so what I like to do is figure out how far is the change in x. That should be 12. You could look at it this way too. 6 to negative 6, that's your change in x. That's 12 spots. Now, from here to here is your change in y, and that's going to be 9 spots if you count it. Or, again, negative 2 to 7 is 9. All right. Now, that's not going to be easy. This is the first time in a while we've seen a decimal. So here's what I want to do. I'm going to look for each equal part. If the change in x is 12, here's what I'm going to do. I'm going to take 12 divided by 6 to get 2. So the change in x for each one is going to be 2. 2 each for the change in x. Okay. We'll come back to what that means in a minute. Now, 9 divided by 6 is 1.5. That means each for the change in y. Now, here's what I mean by that. I'm going to slide over 2 in x and up 1.5 for y. Now, that's going to get me my first point as far as changing it into 6 equal parts. Now, from here, I'm going to go 2 and 1.5. There's the next one. 2, 1.5. 2, 1.5. Now, what I just did was I created, if you look at this, I created 6 equal parts. Now, I need directed segment from x to y. Okay, we have to go in this way, and we have to make it 1 to 5, so we got to go right there. That location right there. Okay, get rid of some of that scribble. Where did I go here? Right there. All right. So that location right there is the one we're looking for, because it's going to make it 1 equal part and then 5 equal parts. So whatever that is 1, 2, 3, 4, negative 0.5. Negative 4, negative 0.5. And that looks like right there. Okay, so that's what it looks like. 19. All right, 108 there, 108 there. Area of a sector, okay, we want pi r squared for the area of this full circle. Pi r squared for the full circle. But then we have to, for the area of the sector, what I like to do is I like to do pi r squared times your fraction part over whole. What that would mean in this case, pi r squared, and then it's going to be the 108 divided by 360. See, we want to go 108 degrees, okay, 108 degrees of this circle out of a full circle, which is 360. So this is kind of like part over whole. Now, when you reduce 108 out of 360, let's see. Okay, we could go 36 times 3, 36 times 10. That'll reduce to 3/10. Okay. All right, so which ones are like that? Okay, we got our 3/10, we got our pi, and BC. Oh, BC is not the radius. See, if that were 60 degrees, we could use BC. We can't use Amy's. All right, this is not the radius. BC is not the radius. 108 pi, we got 108 over 360, and pi and OC squared. That's perfect. That's 108 over 360 pi r squared. This is strange. Okay, half of AB is the radius. So Carl's got it good too. Something's wrong with dexes. They squared the diameter and then took half. That's not going to work. Okay, you're gonna get something that's twice as much as you should. So which one's Beth and Carl? That's what we're looking for. All right, not easy. Okay, the cylinder. How many? Okay, so we have a cylinder. All right, and we want to fit 4 tennis balls diameter. Okay, so basically what's going to happen is this is going to be 4 diameters tall, 1 diameter across. So it's going to be 6.7 for the full diameter. What's 4 times? Let's see, that's 26.8. Is that right? Let me get my calculator. I better get that. Let's see. Yes, it is 26.8. Good. All right, so that's my height. All right, get some space here. Oh, let's see. Four. Okay. All right. Yeah, I don't think we have to do. We don't have to do anything with the spheres. So all we're going to do is pi r squared h. And so, oh, we got to, yep, the radius is going to be half of this. 3.35. So a little trick there, watch out for that. 3.35 squared times our height of 26.8. That should get us a volume of, how much is it? 20 or 944, 875. Yep, that's close enough. All right, 21. Almost done here. Yep, whoa. Okay. Well, to actually perform this is going to be, on the graph is going to be a little crazy. So let me just sketch it quick. All right, 4, -2 is, say, somewhere in here. That's A prime. Yeah. 16, 14 is somewhere way up here, B prime. Okay. We dilated, that's the image. Oh boy. So that's actually smaller. Okay. So we're going to be way out here somewhere. Let's see. So A is going to be somewhere around here, right? Yeah, I think A is going to be at 8, -4. Okay. So that way, because we're centered at the origin, you can just multiply the coordinates. So 8, right, times a half is 4. -4 times a half is -2. So that's where I got that from. And then this is way up here. Okay. This is way up here at 32.28. That's going to be B. Let's see. What is the length of AB? Okay, it's just going to be double of whatever. Oh, never mind. We don't need all this. It's going to be double whatever A prime B prime is. So I'm going to make my right triangle, run Pythagorean Theorem to get that, and then we got to make sure we double it afterwards. So A to B, how tall is that? Looks like 16, right? Because we're going to go from 14 in the y direction to -2. In the x direction, we're going to go from 4 to 16. That's 12. So we're going to go 12 squared plus 16 squared equals d squared. Is that 400? Yeah, 400. All right, that's 20, but AB is twice as long, don't forget. So if this is 20, that's 40. So that's what we wanted. What's the length of AB? All right. These are always, can be very tricky. Here's what we want. Let's pull those out for a second, okay? Let's redraw them separated. It's going to be a lot easier to see things. Okay, so we got ABE, and then we're going to come over here. We're going to try to pull this out too. And we're going to have C and B and D. Okay, it's going to make it a lot easier to look at. All right, DB is congruent to BE. That's what they're telling us right there. And they both use angle B. I'm not going to say it's a right angle. We shouldn't. Yeah, we can't guarantee that. So we do know that angle B's are the same due to reflexive property. So what we have here is a pair of sides. To make this the included angle, so that we can say side angle side, but basically what we need is those two sides the same. Now we already have BD the same as BE, right? All we need is these extra pieces the same, so that we can use segment addition postulate. I can do a triple there. We can use segment addition postulate to get the whole thing. So we need AD congruent to CE, and that's this choice right there. All right, 23. Yeah, this one's pretty common. No matter what we do, if we have a circle and we have a diameter, right? It doesn't matter where we place this other point. We're always going to get a right angle. Doesn't matter if we place the point there. Okay? Doesn't matter. If it goes through the center, it's a diameter. We could place it right here. We can move it anywhere we want, and it's always going to be a right angle. Okay, so an inscribed angle that opens up to a diameter always produces a right angle. Okay, so wherever we put, wait a minute, D, okay, triangle BCD must be a right triangle. So there it is. All right, last one for this batch, for the part ones. All right, parallelogram to start with, that's good. And we have CE congruent to BE. There it is, 112. Okay, since we have a parallelogram, that is 112. Opposite angles of a parallelogram are congruent. All right, so then I'm going to go 180 minus 112. There's probably a better way, but this is what I see right away. So that's 68. I'm going to use base angles theorem, right? If these two sides are the same in a triangle, and that's 68, then this one's 68. That looks like 136. And then the three angles of a triangle add to 180. So we're going to get this angle right here is 44, and that's what we wanted. All right, so that's it for the part ones on the August 2016 exam. Thanks for tuning in. Go ahead and subscribe or like the page or both. Thanks so much.